Hello friends, so let us continue our discussion on the imperfections. So in the previous lecture, we saw that because of the regular arrangement of the atoms in the crystalline material, any deviation from this regular arrangement of the atom is categorized as defects. So if you want to identify defects, then we need to have the regular arrangement of the atoms, and since in a crystalline material we have such a regular arrangement of the atoms, so any deviation from this regular arrangement we refer to as the defects, and these deviations we refer to as the imperfections. Now, depending on the degree of the imperfection, how long this imperfection extends in the crystalline arrangement, we classified defects into three types. So one is the point defect, the other is the line defect, and the third one is the surface or volume defects. So the point defect, it is confined to few atomic spaces, one or two atomic spaces largely. The line defect extends beyond this atomic spacing to a particular one dimension or along a line or along a one dimension. The surface and the volume defects, they extend beyond the one dimension to two or three dimension conditions. So the imperfection, depending on how extensive they are in a crystalline material, we categorize them into point, line and surface. Point defect, it might be referred to as a zero dimensional defect because it is confined to a point with two or one or more atomic spacings. The line defect, it is one dimensional in nature. The surface is two dimensional and volume is three dimensional. So these are the ways we can classify the defects or the imperfections in a crystalline material. Again, it is possible for us to identify defects in the crystalline material because every crystalline material is characterized by a long range regular arrangement of the atoms. Any imperfection in the long range regular arrangement of the atoms is because of these defects. Now, in the previous lecture or the end of the previous lecture, we focused largely on the point defects. We showed that there are two possible point defects. One is the vacancies, the other is the interstitial atoms. Now, the point defects, or particularly the vacancies or the interstitial atoms, are possible for us to identify because in a crystalline material, the atoms, they occupy a specific positions. Only when we are able to understand or we are able to realize the specific positions of the atoms, only in that case we will be able to realize the vacancies or the interstitial atoms. So similar to the criteria that helps us understand the possibility of the defects, in case of point defects there is also another additional criteria, that is the atom occupies specific positions in the crystalline material, and these positions we call as the lattice sites, and the positions that are away from these lattice sites are the non-lattice sites. That are away from this lattice sites or the non-lattice sites are the interstitial positions. When a lattice site is vacant, we refer to that as the vacancies. When the atom that is supposed to be in the lattice site, it moves away from the lattice site and occupies a non-lattice site position or the interstitial position, we refer to as that as the interstitial atoms. Now at the end of the previous lecture, we added to this description of the interstitial atom a term self to indicate that it is the atom that is supposed to be present in the regular lattice position that is occupying the interstitial site. So that is the reason, or that we refer to as the self-interstitial atoms. So all these referred to are largely observed in dilute solid solution or pure crystalline metals. So these point defects, they are largely characteristics of, or they are characteristically observed in pure metals or very dilute solid solutions. So reason we consider pure metals largely because in these pure metals we are fairly sure of the atomic positions or the positions wherein the atom should occupy. So we are fairly sure of the lattice sites, and only when you are fairly sure of the lattice sites you will be able to realize the point defect. Now when you consider a solid solution or an alloy wherein you have intentionally added some alloying element that occupy the interstitial position. Now, the reason certain alloying element occupy the interstitial position, this you might already be familiar with, is because of the difference in the atomic radius. Now, when you have an alloying element which has a very small atomic radius when compared to the actual metal or the base metal, then the alloying element occupies the interstitial position. So that is a different form of a point defect. So the point defect is categorized into intrinsic and extrinsic point defect. Intrinsic and extrinsic point defect. Now, in case of intrinsic point defect, what you observe is the atoms of the pure metal, the atoms of the base metal, either they are missing or they occupy the interstitial site. So this is what categorizes the intrinsic point defect. Intrinsic point defect, it is the atoms of base metal that is missing or occupying non-lattice site. In case of extrinsic point defect, the condition that is necessary to have an extrinsic point defect is the presence of impurities or alloying elements. So the extrinsic point defect is possible only when you have impurities or alloying elements. So only in the presence of this an additional alloying elements or an additional impurities, we have extrinsic point defects. So the point defects can be intrinsic and extrinsic. In case of intrinsic, the defects, the missing or vacancies or the interstitial atoms is largely due to the missing of the atoms in the missing of base metal atoms or the replacement of the base metal atoms. In case of extrinsic point defect, you have impurities or the alloying elements that are present. So the interstitial atoms, now in case of interstitial atoms, in case of the extrinsic point defects would be alloying element atoms. So in case of intrinsic, it will be self-interstitial. In case of extrinsic, it is the alloying elements that occupies the interstitial position. Now, it is also possible that the size of the alloying element can be comparable to that of the size of the base metal. So the atoms can occupy also the regular lattice position, and those atoms will be substitutional arrangement. So in this we have in the substitutional arrangement, we have an alloying element. The size of the atoms of this alloying element is comparable to that of the size of the atoms of the base metal, and therefore this alloying element is, or the atom of this alloying element is present in the regular lattice, and this disturbance or this imperfection in the regular arrangement of the atom is referred to as the substitutional defect. So the substitutional arrangement of the atoms leads to the substitutional defect. So in case of point defects, depending on the composition of the crystalline material that we consider, it can be intrinsic point defect or it can be extrinsic point defect. So the intrinsic point defect, it is the base atoms as of the base metals that is either replaced or is missing from its lattice position. In case of extrinsic point defect, it is the atoms of the alloying element which is occupying the interstitial or which is occupying the interstitial site or which is replacing the base metal atoms in its regular lattice site. So these are the two distinctions that one can make within the point defect. In case of extrinsic, it is only possible when you have impurities or alloying element. Now these alloying element, depending on the size of the atoms of these alloying elements, the atoms either might occupy the interstitial lattice or interstitial site, which is also referred to as the non-lattice site, or this alloying element or the atoms of this alloying element can replace the base metal atoms in its regular position, and depending on where the atoms of this alloying element occupy the lattice or occupy the arrangement of atoms, they are referred to as the interstitial atom defects or substitutional defect. So interstitial defect or substitutional defect. So this again depends on the size of the atoms of the alloying element. So atomic size of the, depending on the atomic size of the alloying elements, we have intrinsic or extrinsic interstitial defect and extrinsic substitutional defects. So these are the different forms of point defects that we observe depending on the composition of the crystalline material. So intrinsic or the extrinsic is only possible when you have sufficient amount of alloying element or impurities. Now let us go back to the point defect, particularly the intrinsic point defect, to have some basic understanding. In order to gain some basic understanding on the point defects as a whole, let us go back to the intrinsic case. Now, the factors that contribute to the formation of the intrinsic defects are, there are various factors that could contribute to the formation of intrinsic point defects. So these factors, they include plastic deformation or nuclear irradiation. So largely these two factors, they contribute to the formation of point defects in a material, or in a material that is close to being pure. Or when you talk about intrinsic point defect, these two factors or external factors, they largely contribute to the point defects that we observe, both vacancies and interstitial atoms. So the plastic deformation, we will see that plastic deformation involves a shift in the position of the atoms. So therefore it is possible for the plastic deformation to introduce or to displace the atoms from its position, thereby introducing the point defects. So that is, it is fairly straightforward to understand how a plastic deformation brings about a shift in the position of the atoms, thereby bringing about the point defect. The other way how the point defect can be introduced is through nuclear irradiation, wherein a high energy particle impinges on the crystalline arrangement of the atoms. Because of this interaction between the high energy particles to which the crystalline material is exposed to, you would have a change in the positions of the atoms. So this change in the position of the atom, there might be the formation of the position of the atoms, or the atoms of the base metal might shift in its position to an interstitial position, thereby leading to an interstitial defect in the intrinsic or in the pure metal, or the atom might move away from the system as a whole, thereby leading to the formation of vacancies. So as a whole, or the major contributors to the formation of the point defects are the plastic deformation and the nuclear irradiation. Now, in addition to these external factors, it is also observed that with increase in temperature, these point defects also increase. So the temperature, just by increasing the temperature of the material, the point defect also increases. So what we essentially have is, in addition to the external factors contributing to the point defects, we have the internal change in the material that leads to the, or that introduces the point defects. Moreover, it is stated that any temperature above the absolute zero, so any temperature above 0 Kelvin, we would have a stable amount of, or an equilibrium composition of these point defect. So when you have a temperature that is beyond the absolute zero, there is a stable composition or a stable concentration of these point defect, that is the vacancies and interstitial atoms that are possible within the system. So when you increase the temperature, what you are essentially doing is you are imposing a thermal energy into the system, and this thermal energy helps in introducing the point defects, and therefore any temperature above 0 Kelvin or above absolute zero, you would have an definite stable concentration of point defect. Now let us see what is the thermodynamic basis for having the stable concentration of vacancies or interstitial atoms, because whenever we talk about imperfections or whenever we talk about defects, it is nothing but the irregularity in the regular or in the arrangement of the periodic arrangement of the atoms. So we define defects as the irregularities, imperfection in the regular arrangement of the atoms. So if we assume the regular arrangement of the atoms as the lowest energy state, then the imperfection then should be the increase in the energy state. So the low imperfection then should be a disturbance to the lowest energy state. However, we observe that these point defects are stable at temperatures above 0 Kelvin. So there should be some thermodynamic basis that allows for a stable concentration of this point defects. So let us look into that thermodynamics basis. So to reiterate, the regular arrangement of the atom in the crystalline material is the lowest energy state. So any imperfection to that lower regular arrangement of the atom means we are increasing the energy state. So it means the system is no longer stable. However, any temperature above 0 Kelvin or absolute zero, we have the stable concentration of vacancies. So let us see how these vacancies, which are supposed to be the imperfection, which are supposed to raise the energy state of the crystalline material, is stable at temperatures that are above 0 Kelvin or absolute zero. Now, supposing you have n point defects. So n here is the number of point defects that you have, and EFB the energy required for the formation of these point defects. Formation energy, or the energy required for the formation of this point defect. Now as of now, we don't want to distinguish the point defects into vacancies and interstitial atoms. We will do that subsequently in a few minutes, but for now, for this discussion, let us consider point defects as a whole. Let us assume there are n point defects, and the formation energy or the energy required for formation of these point defects will be EF. Now the change in the Helmholtz free energy. So the change in the Helmholtz free energy will be delta F. So this will be change in the free energy. I hope you are able to have some idea on the difference between Helmholtz and Gibbs free energy. Maybe you can brush that difference up. So let us assume that because of the introduction of the point defects, we have a change in the Helmholtz free energy. So this change in the Helmholtz free energy, delta F. Now because since these point defects are a disturbance to the regular arrangement of the atoms, a disturbance to the stable arrangement of the atoms, this means when you have this point defects, your energy of the system as a whole increases. So these point defects, they increase the energy of the system. So they render a positive contribution. So we have this contribution, that is the product of number of point defects that are present and the energy required to forming this point defect. So this combination increases the overall free energy density of the system. However, if there is a change in the entropy because of this introduction of the point defects, then through this relation you have a decrease in the overall energy density of the system. So what we essentially have is, we essentially have a contribution from the number of point defects that are present. So with increase in the number of point defects and for a given energy required for the formation of the point defect, the combination of these two increases the overall free energy of the system. However, when this point defects, the introduction of this point defect, when it also increases the entropy, then the overall free energy is reduced. So therefore, if left on its own, if we are not considering the effect of entropies, then the introduction of the point defects is unstable. Supposing if you are not considering the role of entropy or the change in the entropy, then the introduction of point defect alone will increase the free energy of the system. So that means it is an whatever point defects we have, it is unstable. But since we have the contribution of the entropy, and particularly there is a part or an aspect of entropy that is called as the configurational entropy, with increase in the point defect, this configurational entropy or the entropy as a whole increases. Therefore, beyond certain limit, when the configurational entropy is sufficiently high, when the combination of temperature and configurational entropy is sufficiently greater than the change in the energy density that is introduced by the point defect, then you have a decrease in the overall energy density of the system, and in this case we have stable point defects. So what we essentially have is a thermodynamic condition that tells us under certain there is a possibility for the point defects to be stable. So this possibility is when we consider the influence of the point defects on the entropy. Supposing if you consider the point defects alone, then with increase in the point defects, we have an increase in the energy density or the free energy of the system. So that makes the system totally unstable. However, when we include the influence of the point defects on the entropy, we see that with increase in the point defects, the entropy also increases. So under this condition, when the influence of the entropy on the free energy density is greater than that of the influence of the point defects, then you have a stable point defect. So here the influence of the point defects on the entropy is through the configurational entropy. So let us assume, or let us see what, I will just give you a brief idea on how this point defect increases the configurational entropy. Supposing you have a system, or consider an atomic a crystalline system, and we focus on, let us assume that to be say a simple cubic, and let us focus on the sequence of the simple cubic along the 100 family of planes. So you consider the atomic arrangements in the simple cubic along the 100 family of planes. It's rather straightforward. You would have now even though these touches each other, let us for the sake of this argument consider they are a hard sphere that is less than the radius of the base metal, so that it is not touching each other. Now when all these positions are occupied, these are the atomic positions of the atoms along 100 plane of simple cubic, when all these positions are occupied, then this is the only way you would be able to arrange the atoms. So this is the only way you would be able to arrange the atoms when all positions are occupied. So when all lattice sites are occupied, this is the only way you would be able to arrange the system. Supposing you have one vacant site. So you have one vacant site, that is this. Then it is possible for us to arrange this vacant site in a different manner. So the vacant site can be here. So the vacant site can also be here, and the vacant site can also be here. So when you have one vacant site in a specific plane of a simple cubic structure, the number of ways these vacant sites can be arranged equivalently increases. So here when you have all the sites that are being filled, you just have one way of arranging these atoms. So each atom goes into its corresponding positions. But if you have one vacant site, it is possible for us to arrange this vacant site in any of these positions. You have 4 ways of arranging it. So 1, 2, 3 and 4 ways of arranging it. So this is what leads to an increase in the configuration. This is what is referred to as the configurational entropy, and this configurational entropy is possible because you have one vacancy here or one point defect here, and this is what is referred to as the configurational entropy. This is just a very straightforward or a simple description of the point defect. Of course, you have to have, there are expressions that discuss this configurational entropy, that is of a statistical mechanics based. So in order to show that how the point defect increases the entropy, I just gave you this rather a schematic representation of how a presence of vacancy increases or introduces configurational entropy. So when you have a system wherein all the atoms or all the sites are being occupied by the atoms, then you have only one way of arranging the atoms. However, when you have one vacancy introduced and just one vacancy in this particular plane of a simple cubic structure, you have 4 ways of arranging it, and this is nothing but the increase. This indicates an increase in the configurational entropy, and therefore in this expression, when there is an increase in the configurational entropy, the overall energy of the system decreases, thereby making the point defects stable. So because of this influence of the point defects on the configurational entropy above 0 Kelvin, because when you consider 0 Kelvin here, you have completely at 0 Kelvin, say when you have 0 Kelvin here, you have completely ignored the role of configurational entropy, and therefore with increase in the point defects you have an increase in the overall energy density of the system. However, above 0 Kelvin, since this term becomes non-trivial, this term plays a role, then with increase in the configurational entropy, it is possible for us to have stable point defects. So this is the reason why, even though the point defects, they disturb the regular arrangement of the atoms, they disturb the stable or the low energy state of the atom, they are stable at temperatures above 0 Kelvin. They are stable through their influence on the entropy. So we have now above 0 Kelvin the stable concentration or the stable point formation of point defects. Now let us see how one could express the stable concentration of this point defect. Now the stable concentration of a point defect at a temperature or at a given temperature is expressed in this manner. So if we consider vacancies, the stable concentration of vacancies at a given temperature is expressed as EF minus of EF, rather let us as EV minus EV by kappa T. So this is an expression that tells us how much amount of stable vacancies that are present at a given temperature T. So at a given temperature T, this is the temperature, and K is the, or kappa is the Boltzmann constant, or let us call it as K, it's the Boltzmann's constant, and EV is the energy required for the formation of vacancies. So what we essentially have is energy required for the formation of vacancies and temperature. So depending on the energy required for the formation of vacancies and the temperature. So this is a material property. This depends on the material that we are considering. So this is an external agent, the temperature that we vary. So depending on the combination of these two, we can have a stable concentration of vacancies. So this CV here is the number of vacancies divided by the total number of lattice sites that are present. So N is the total number of lattice sites that are present, and NV is the number of vacancies. So the stable concentration of the vacancy, it depends on energy required for the formation of vacancies and the temperature. Now this relation indicates that with increase in the temperature, the number of stable vacancies also proportionately increase. So we have a negative sign here, exponential, a negative sign here. Therefore, with increase in temperature, we have a increase in the stable number of vacancies. So these vacancies, even though they increase, they are still stable. And here with increase, again with increase in the number of, or with increase in the energy required for the formation of vacancies, the number of vacancies, they decrease. Now when you want to write a similar expression for the interstitial atoms, so when you want to write a similar expression for the interstitial atoms, the parameter that you need to change is EV to EIN, because the energy required for the formation of vacancies is not equal to that of the energy required for the formation of interstitial atoms. As a matter of fact, the energy required for the formation of interstitial atoms is close to or approximately 4 times that of the energy required for the formation of vacancies. In this discussion here, we've been considering just the point defect as a whole, N as a point defect as a whole. However, here we are differentiating vacancies and interstitial atoms. This is primarily because energy required for the formation of vacancy is less than the energy required for the formation of interstitial atoms. And if you want to compare, or if you want to quantify the difference between the energy required for the formation of vacancies and the energy required for the formation of interstitial atom, it is this relation, it is close to that of 4 times the energy required for the formation of interstitial atoms is close to that of 4 times the energy required for the formation of vacancies. So under such a condition, when you substitute this in here, or when you have an expression for the amount of, or the concentration of interstitial atoms at a given temperature, it would look something like this: exponential minus EIN and kappa T. And when you substitute this here, and when you compare the CV, the concentration of, or the stable concentration of vacancies and the stable concentration of interstitial atoms, then you would observe that at a given temperature, the concentration, or the stable concentration of vacancies is significantly higher than the stable concentration of interstitial atom. And this primarily stems from the relation that the energy required for the formation of interstitial atom is significantly higher than the energy required for the formation of vacancies. It is close to 4 times. So this is again an experimental observation. So when you have such a condition, then the formation of stable number of vacancies at a given temperature will be significantly higher than the formation of the stable number of interstitial atoms. And therefore, when point defects are considered, or when stable point defects are discussed for a particular temperature, it is largely confined to the concentration of vacancies, and the concentration of the interstitial atoms is overlooked. So when you want to talk about the stable concentration of point defect at a given temperature, it is largely focused on the concentration of vacancies. Again, you have to remember here, we are talking about the influence of temperature on the point defects. We are talking about the stable concentration of vacancies at a given temperature. So under such condition, since the energy required for the formation of the interstitial atoms, or the self-interstitial atoms, is significantly higher than the energy required for the vacancies, and the concentration is dependent on the exponential relation, we have for a given temperature a significant amount of stable vacancies when compared to the interstitial atom. And therefore, when one talks about stable point defect at a given temperature, they are largely focusing on the stable concentration of vacancies. It does not mean we give equal importance to vacancies and interstitial atoms at a given temperature. The point defect at a given temperature, a stable point defect at a given temperature, is largely due to vacancies rather than the interstitial atoms. So even the interstitial atoms, we cannot give equal amount of, we don't observe even equal amount of interstitial atoms at a given temperature. The point defects is largely confined to vacancies at a given temperature. Now, so we say that the vacancies is the missing of an atom, or the atom that needs to be present in a specific position of the lattice is missing. So where does this atom go, or what is the conventional way of describing a vacancies? So we cannot just say an atom is missing from a spot. We have to know where this atom goes. So the conventional way of discussing or describing a vacancy is that the atom during a vacancy, or during the formation of the vacancies, the atom, it moves from its lattice site to the surface. So the energy for the formation of vacancy, it is calculated by considering the movement of the atom from the lattice site to the surface. So that is how we define the vacancies. And the interstitial atom, or the energy required for the formation of the interstitial atom, we define it by considering the reverse movement of atom from surface to an interstitial position. So the vacancies, in case of vacancies, we have atoms moving from the lattice position to the surface. In case of interstitial atoms, in case of the point defects wherein we have atoms occupying the interstitial site, these atoms, they come from the surface. So the energy required for the formation of the interstitial atom is calculated by considering the amount of energy that is required to shift an atom from the surface to the interstitial site. Since the interstitial site is present in between the lattice sites, since in order to place or take an atom from the surface and putting it in the interstitial site requires a huge amount of energy, that is why we have a relation that states that the energy required for the formation of the interstitial atom or the formation of or placing the atom at the interstitial site is significantly higher than the energy required for placing the atom or removing the atom and placing it in the surface. Now in the surface you have an additional degree of freedom, and so you can place the atom fairly easily on the surface. However, placing an atom within the interstitial site between the lattice points or in a non-lattice site, it requires a huge amount of energy, and that is the reason why we have the energy required for the formation of interstitial atom considerably higher than the energy required for the formation of vacancies, because placing an atom in the surface wherein you have additional degree of freedom is fairly easier than placing an atom within the interstitial site, wherein you are already surrounded by the sufficient number of atoms, and that's the reason you have this significant disparity in the energy required for the formation of interstitial atoms and the energy required for the formation of vacancies. Now, because of this difference in the energy required for the formation of interstitial atoms and the vacancies, you have significant difference in the concentration of the vacancies at when compared to the interstitial atoms at a given temperature. Now, what we have so far been doing is we have largely focused on the interstitial, or rather the point defects, focusing on the vacancies and the interstitial atoms, and we have seen that this point defect for a given temperature can be stable. Now let us move into the other form of the defects, particularly the line defect. Now the line defect, as we have seen earlier, it extends, or the influence of this line defect, it extends beyond few atomic spacings or few atoms. Now when we talked about the vacancies, like we have considered, so this vacancy, if you have an atom missing at this spot, so it is confined to this atomic position, and if you have an atom that is being placed in this non-lattice site, so it is confined to this region here. So meaning the point defect is largely associated, so this is the interstitial atom and this is the vacant site. So the point defect is largely associated with, or its influence is largely with respect to few atomic spacing. However, when we consider the line defects, its effect or its influence, it is beyond few atomic spacing, and it extends on a particular or along a particular dimension, and that is the reason why we call that as the line defects. Now the reason we are focusing on the different forms of defects is because these defects play a vital role when you deform the material. We are considering these defects again in the context of the mechanical behavior of the material. When we want to study how the mechanical condition that we impose on the material changes the material, then we have to understand how to quantify the change in the material, particularly at the atomistic level. We want to know what are the ways to describe a change that is introduced in the atomic arrangements when you impose a mechanical condition. So one way we saw is that when you impose the mechanical condition, it is possible for the atoms to move away from its position or leaving an empty site, that we refer to as the vacancies, or it is possible for the atoms to occupy a non-lattice position that we refer to as the interstitial defect. Now we are moving away from this point defects to the line defects, and particularly there is one line defect that plays a dominant role during plastic deformation. So that line defect we will reserve it for later, but now we will consider another point line defect that plays a vital role during plastic deformation. Now one reason we are considering, in addition to these defects help us describe the influence of mechanical behavior or the response of the mechanical condition on a material. In addition to that, these defects help us to describe the response of a material to a mechanical condition. It is also that these defects influence how a material behave to an imposed condition. So depending on the presence of this defect or the absence of this defect, the response of the material or the behavior of the material would vary, and that is one of the other reason why we are considering we are taking some time to discuss these defects. So let us consider a line defect that is observed during the plastic deformation, but is not as dominant as the one we will be considering in the next lecture. So we will be let us now consider one of the line defect that is observed or that influences the behavior of a material under a imposed mechanical condition. So when we consider or when we defined a defect, we began with a criterion. So when we want to define what a defects are as a whole, we began by considering that only when you have a regular arrangement of the atoms, we will be able to identify the defects. When you don't have the regular or periodic arrangement of the atoms, it will be difficult for us to then identify the imperfections in the regular arrangement and to quantify the defects. Therefore, when we want to identify a defect, then we should start from the regular arrangement of the atoms. Secondly, when we discussed or when we want to identify point defects, we saw that each atom should occupy a specific position for us to identify the point defect. If the atomic positions are random, we will not be easily able to identify the point defects. Only when you have atoms occupying a specific position, you will be able to notice the lack of an atom in a given lattice site or the presence of an atom in the non-lattice site position. So these are possible only when you have a clue or a fairly elaborate idea on the positions of the atoms or the lattice sites wherein the atoms should be present. Now, in order to describe this line defect, we need to have an idea of the arrangement or the stacking of atoms along a particular plane. So these line defects, we will be able to identify them only when we are familiar with the stacking sequence of the atoms in a given plane or under direction of a particular crystal structure. So we have seen that for a given crystal structure along a definite plane and a direction, you have a regular arrangement of the atoms. You can arrange the atoms, you can present the atoms in a way such that you will be able to realize or you will be able to express the overall crystal structure based on stacking the atoms along a particular plane. Now we saw there are various ways of describing the stacking sequence, and the way that we would describe a particular stacking sequence is to see if the arrangement of the atoms in the subsequent layer that is built on the fundamental layer, the subsequent layer is similar or different from the first one. Now if it is similar, we use the same nomenclature. If it is different, we use a different nomenclature. So in that case, the different stacking sequence that we saw are of this form: AB, AB, and so on. And the other sequence that we saw is ABC, ABC, and so on. Now these are the two stacking sequence that we largely observed in the face-centered cubic materials. So along a particular family of planes, that is 1, 0, 0, we observe this stacking sequence in FCC. Along 1, 1, 1 family of plane, we observe this stacking sequence in FCC. Now, if there is any disparity in the stacking sequence, supposing we are focused on the stacking of atoms along the 1, 1, 1 family of planes. Now in this family of plane, wherein there should be this particular stacking of atoms, that is the second arrangement or the second layer of atoms along this particular plane should be different from the first layer, and the third layer of atoms should be different from both first and the second. So this characterizes the stacking sequence of atoms in FCC along 111 plane. If there is any disturbance in this stacking sequence or in this arrangement of the atom, supposing instead of C here we have an arrangement that is A, B, C, A, B, A and B. So the C here is missing. The third, or rather the sixth layer, which should be equivalent to that of the third layer, instead of being equivalent to that of the third layer, becomes equivalent to that of the fourth. Then you have a fault or a defect in the stacking of the atoms, and this is referred to as the stacking fault. So we are now considering, we have now moved away from the point defect, we are considering the line defect, and we are largely focusing on one of the line defects. There are numerous forms of the line defects. We are considering one of the line defect. Now the criteria that helps us to identify this particular line defect is the arrangement of the atoms when you stack one layer over the other. Now if you consider, say for instance, FCC crystal structure, and you are stacking the atoms along the family of 111 plane, one over the other, the stacking sequence should be ABC, ABC and so on, meaning the fourth layer of the atom should be equivalent to the first layer, the fifth should be equivalent to the second, and the sixth should be equivalent to the third. Now instead of such an arrangement, you see a disturbance, meaning as we have considered here, the sixth layer of atoms, which should be equivalent to that of the third, is now equivalent to that of the fourth or equivalent to that of the first. Then you are now observing a defect in the arrangement of the atoms, and this defect is not confined to a point, but it extends over the line, and this we refer to as the stacking fault. This is significantly different from what we observe in the point defect. It is not, that is the defect, it is not a defect that is associated with a given atomic spacing, but this is a complete shift in the arrangement of the atom. And now since the shift does not mean that we are replacing the whole of the atom, but this shift is just a small change in the position of the atom, we refer to this as the stacking fault, and we categorize this under the not under the area or the surface defect, but we categorize this under the planar defect. So this comes under the, not under the surface or volume defect, this comes under the planar defect. What we observe is the change in the arrangement of the plane in a particular, arrangement of the atoms in a particular plane, and this we refer to as the stacking fault. So now what we have done is we have moved away from the point defect, we have moved into the line defect or a particular advancement in the line defect, which we refer to as the planar defect. Now this planar defect is possible for us to identify only when we know the sequence of the arrangement of the atoms based on a particular layer within a crystal structure. So we will build on this form of defect in the subsequent lecture. So let's see ourselves in the next lecture where we will be building on this form of defect. Goodbye.